This is Coach Storr. I'm going to talk about the mean value theorem. Before we get into the mean value theorem, which is a very important theorem in calculus, we're going to talk about a preliminary theorem called Rolle's theorem. Here are the conditions of Rolle's theorem. Let f be a function that is continuous on a closed interval from a to b. Also let f be differentiable on the open interval from a to b, and let f of a equal f of b. Remember, f is continuous on a, b. You can think of that as meaning that I can draw the graph of f without lifting my pencil. And if f is differentiable, that means that it's continuous, which we already have in part A, but also that it's not going to have any corners or cusps, and it won't have any vertical tangents. So let's just look at some images of some possible that could be satisfying the conditions of Rolle's theorem. So I could have a graph of a function that looks like this. Okay, where here is x equals a and here is x equals b. And we notice that graph of my function doesn't have any corners or cusps, no vertical tangents, so it's differentiable. It's definitely continuous because I was able to draw it. And the f of a value equals the f of b value. That's saying that this, here I'll mark it in red so it's easier to see here, that this point has the same y value as this point. All right. Here's another possible example of a function that would work. Okay, let's suppose I have a function that looks like this. All right, there's my x of a, there's my x of b. My graph of my function is continuous there. I was able to draw that without lifting it up, so the function is continuous from a to b. It's also differentiable, no corners or cusps, and the value, again, of f of a, there's f of a point, and there's f of b. Those have the same y value there, so it works. So when I have those conditions, what are the results? The result of the Rolle's theorem. Well, it says that there's a number x equals c, where c is between a and b, such that the derivative at c equals 0. All right. So what does that mean in terms of our graphs here? We'll go back to the blue graph. If the derivative at value c equals 0, that means that the slope of the tangent line is equal to 0. So it's a horizontal tangent line. Well, that happens like right here. There's my horizontal line. So there's the derivative at c equals 0. And the c value is going to be right there. There's x equals c. All right. So Rolle's theorem tells me that there is this number c somewhere between a and b, so that if I took the derivative of the function at that point c, then I would get the derivative equal to 0. So the tangent line is horizontal. If I look at the my second example there, you can see that, well, I got a horizontal tangent line there, and I got one here, and I've got one here. And so there's actually going to be several c values. I'll call them c1, c2, c3, that all work. That the derivative c1 equals 0, the derivative at c2 equals 0, and the derivative at c3 equals 0. You get horizontal tangent lines there. So Rolle's theorem says there is at one. There could be more than one, as we see in the second example here. There were three, but there's at least one that works. Okay, let's look at this example of this with a specific function. So we're going to let f equal the sine function, and we're going to be on the interval from negative pi over 2 to 3 pi over 2. So what's the graph of the sine function look like? Well, it goes to the origin, and it's like a wave here, going up and down like that. And let's put in some values here. This point here is over 2. Here we have 3 pi over 2. Here we have negative pi over 2. All right. And so I'm looking at the interval, we said here, from negative pi over 2 to 3 pi over 2. So I'm going from here up like this down to there. That's my function on the interval that we have. Now, does that satisfy the conditions of Rolle's theorem? Okay, conditions of Rolle's theorem. Okay, so those are is continuous on pi over 2 to 3 pi over 2. Yep, that's true. F is differentiable on that open interval from negative pi over 2 to 3 pi over 2. Yep, that's true. And f of negative pi over 2 equals f of 3 pi over 2. Well, let's check this one. Let's see. So f of pi over 2 is equal to the sine of pi over 2, sorry, negative pi over 2, which is negative 1. and f of 3 pi over 2 equals the sine of 3 pi over 2, which is also equal to -1. And so these are equal. So the third condition of Rolle's theorem are correct. Okay, so then what do we have? So the result, there is some x equals c, where c is going to be between pi over 2, negative pi over 2 and 3 pi over 2, such that the derivative at c equals 0. All right, so what is c? Well, let's take the derivative of f. So f is sine of x. So that means the derivative is going to be cosine of x. And when does cosine of x equal 0? So when is cosine of x equal to 0? Well, that works for an infinite number of values, but one of those is pi over 2. And pi over 2 is between negative pi over 2 and 3 pi over 2. And on our graph, remember, we have that, here's our pi over 2. If I go up here and I look at that, there is the tangent line. Okay, so the derivative at pi over 2 equals 0, right? So we have back here, we have the derivative of sine. So the derivative of that is cosine, and the derivative at pi over 2 is going to equal the cosine of pi over 2, which equals 0. And so that means c equals pi over 2. Are there any other values between negative pi over 2, 3 pi over 2? Any of those c that work? There aren't. Okay, there are some other values that work, but they're not between negative pi over 2 and 3 pi over 2. All right, so let's look at a second example here. All right, suppose I have this f of x is this polynomial, x cubed minus 2x squared minus 4x plus 2. And we're on the interval from -2 to 2. And we're supposed to here find the value of c that satisfies Rolle's theorem. Okay, so what do I do? First of all, I have to check that f satisfies Rolle's theorem's hypotheses, okay, which are, again, one is continuous on -2 to 2, and then the second one, f is differentiable on the open interval from -2 to 2, and f of -2 equals f of 2. So let's check these. Well, is f continuous? Yeah, my function f is a polynomial, and polynomials are always continuous, so we're good there. F is differentiable, yep, because it's a polynomial again, it's differentiable. And f of -2 equals f of 2. Well, let's check that. What's f of -2? So I'm going to put -2 into the function. So I get -2 cubed times 2 times -2 squared minus 4 times -2 plus 2. That's going to equal negative, and sorry, I got there, I'm at -2. Then I have -2 squared, which is 4, times -2 is -8. And then I've got -4 times the -2, which would be +8, and then +2. And that's going to be then equal to -6. And now let's look at f of 2. So I've got 2 cubed minus 2 times 2 squared minus 4 times 2 plus 2. So I've got 8 minus 2 squared is 4 times -2 would be -8 there. And then I have a -8 plus 2, and that also equals -6. And these are equal. So the third condition of Rolle's theorem works. All right, so now find c. Well, how would I find c? And I do that by take the derivative of f. So what's the derivative here? Again, my function, rewrite my function. My function f of x is x cubed minus 2x squared minus 4x plus 2. So the derivative is going to be 3x squared minus 4x minus 4. And so what I need to do is I want to set that equal to, because Rolle's theorem says the c value is going to equal 0. And now we're going to factor this. So when I factor this, I'm going to have a 3x and an x here. And it will be a +2 and a -2. And I can check this. So 3x times x, 3x times x gives me 3x squared, x minus 2 minus 6x. A 2 times x is positive 2x, and a 2 times a -2 is -4, and that equals 3x minus 4x minus 4. so it checks. Okay, so I've got that derivative equals 3x plus 2 times x minus 2, and that's going to equal 0, because Rolle's theorem, we want to find the values for where the derivative equals 0. So that means 3x plus 2 equals 0, which then if I solve for x, bringing the 2 over to the other side, get a minus 2, and dividing by 3, I get a minus 2/3, and x minus 2 equals 0, bring the x to the other side, get x equals 2. So which one of these are within the interval? My interval is the interval from -2 to 2. Well, there's got to be at least one of these, and that one works. X equals -2/3 is, so notice that 2/3 is between there. So C equaling -2/3 works. Okay. What about 2? X equals 2. Does that work? Does that work? So note x equals 2 does not work because it's not, because it is not in the interval from -2 to +2 with an open bracket. In a closed bracket it would work, but not in an open bracket, because that x equals 2 is the end of the point there. So my answer is here. So C equals -2/3 is my answer. But let me do one more example of this. So now we're going to let f equal x to the 2/3 on the interval from -1 to 1. Okay, suppose we just go ahead and I just say, well, okay, let's just go ahead and take the derivative and do Rolle's theorem. So the derivative is going to equal, by the power rule, I bring the 2/3 out front. I subtract 1 from the exponent, so 2/3 minus 1 is a minus 1/3. And now since I have a negative exponent there, I can write that as 2/3 times 1 over x to the positive exponent. So it's like 2 over 3x to the 1/3. And Rolle's theorem would say that that derivative equals 0. That would imply then that 2 over 3x to the 1/3 equals 0. But wait a minute, that doesn't work, right? Because if a fraction equals 0, that means that the numerator of the fraction has to be 0. But it's a 2, and 2 doesn't work. So this doesn't work. Okay, so what's wrong? Well, we didn't check the hypotheses of Rolle's theorem. We didn't check those. Check the hypotheses of Rolle's theorem. What are those hypotheses again? Okay, well, the function has to be continuous, it has to be differentiable, and that the endpoints have to equal each other. Well, let's look at the graph of this. So let's see, go back here, and I will share, oops, I bring this up here. I bring up Desmos. Okay, if this works. Okay, now you see the graph here of our function x to the 2/3. Well, you can see that the function is continuous, but it's not differentiable at the origin there. There's a cusp or point there. Okay, that's the problem there. Why we can't get there's nowhere on here where the derivative of the function is going to be have a slope 0. Okay, the derivative never equals 0. I'm not going to get a tangent line that's horizontal here. Okay, is f not differentiable at x equals 0? Because the graph, again, if I were to draw the graph, what we saw on Desmos, the graph looks like this. So here's y equals x to the 2/3, and at there, f is not differentiable there. So we can't use can't use Rolle's theorem. All right, so there's the background on Rolle's theorem. Now this was a preliminary thing. Now we're going to get to the main idea, and this is the mean value theorem. The mean value theorem is more general than Rolle's theorem. Rolle's theorem is a special case of the mean value theorem. You'll see that in a second as we talk about these things. So what do we have for the mean value theorem? Given we have a function, just like we did in Rolle's theorem. And in this case, we have two conditions. We have f is continuous on the closed interval from a to b, and f is differentiable on the open interval from a to b. That's it. Okay, so notice how this is different than Rolle's theorem. In Rolle's theorem, we have a third condition, and that third condition is f of a equals f of b. We don't need it for the mean value theorem. All right, and then the result we get looks a little bit more complicated, but it is it covers more cases than we get with Rolle's theorem. So in here, so like Rolle's theorem, there is a number x equals c. Oh, sorry, that was a mistake there. There's my c, where c is between a and b. Second in Rolle's theorem, such that, and now here's where it's different. The derivative doesn't equal 0, but it's going to equal f of b minus f of a over b minus a. So no, what is that right-hand side there? What is f of b minus f of a over b minus a? This is equal to the slope. And it's the slope of that's connected by the two endpoints of my graph. So if I draw an example here, if I have something like this, function that looks like this, and there's x equals a, there's x equals b. Notice my function, my green graph here, y equals f of x, is continuous and differentiable between a and b. But f of a doesn't equal f of b because f of a is lower, below the x-axis, and f of b is above the x-axis, so they're not the same values. But if I take this line that connects them here, this line here, the slope of that line equals differences of the y's over the differences of the x. And that is what we have here in the mean value theorem. So that sum c is going to have the same value as the slope of the line that connects the two endpoints. And in this example then, where is my c? Well, I want to find a c value between a and b so that if I drew the tangent line, it would have the same slope as the green line. Well, one of those lines would be this right there. And so my c is going to be about there, or down there. And this is equal to the derivative of c, and that has same slope as the green line. And some of you would also notice there's a second point I could have for c, and that would be about here. We'll call that c2. And here, the derivative at c2 equals same slope as green line. So in this case, we got two examples of c values. Just like Rolle's theorem, there's going to be at least one of them, but here we have two. So we're okay. And what the mean value theorem says. So again, in summary, the mean value says that some x equals c value says the slope of the tangent line to y equals f of x at x equals c equals the slope of the line that connects the two endpoints. And how does this relate to Rolle's theorem? Well, in Rolle's theorem, so notice in Rolle's theorem, we have the third condition, f of b equals f of a. So substituting, putting this in to value theorem, and I'm going to abbreviate mean value theorem as MVT. We get the mean value theorem says there's going to be this c value between a and b, such that the derivative at c is f of b minus f of a over b minus a. But if we have that b equals a in Rolle's theorem, then this is going to be 0 over b minus a, which means equals 0. And then we have Rolle's theorem there. So Rolle's theorem is just a special case of the mean value theorem. All right, let's do an example with the mean value theorem then. Oh, yeah, okay, let's do the example. To what we did, we're gonna have a function. We're gonna call this function 1 over x, and we're gonna be on the interval from 1 to 2. And we're gonna show f satisfies the conditions of the mean value theorem, and then we're gonna find d from the mean value theorem. Okay, well, I've got my function f of x equals 1 over x. Again, we're on 1 to 2. Is it continuous on 1 to 2? Well, yes. Where is f not continuous? It's not continuous at 0 because you couldn't have 0 in the denominator, but 0 is not in the interval from 1 to 2, so we're okay with that condition. All right. Is f differentiable on the open interval from 1 to 2? And again, yes, that's okay, because the only problem I would have would be at x equals 0, but that's not between 1 and 2. Okay, so the conditions of the mean theorem satisfied. So let's find c from the mean value theorem. Okay, to do that, we first need a derivative of our function. So what's the derivative of 1 over x? So yeah, let me rewrite that. It'd be better for me to do it this way. I'll start with my function. So as a reminder, f of x is 1 over x. So what's the derivative? The derivative is then going to be I'm going to take the derivative, d dx, x to the negative 1 power. All right, let me write that a little bit nicer. So I'm doing d dx of x to the negative 1 power, and by the power rule, that's going to be negative 1 x to the negative 2, which is negative 1 over x squared. Okay, so there's my derivative. And we also then, first thing we need to do, second, we need to find f of b minus f of a over b minus a. Okay, that's the right side of the result in mean value theorem. So I've got f of 2 minus f of 1 over 2 minus 1. Well, let's see, what is f of 2? Okay, f of 2 is 1 over 2. Okay, so we're going to get 1 here. F of 1 is 1 over 1, which is 1. So I get 1 there. And so I now have this. And so on the top, in the numerator here, I've got 1/2 minus 1, so that's minus 1/2. And in the denominator, I've got 1, so I get negative 1/2. All right, so recall, the result of the mean value theorem is there is a c value, an x equals c, where c is going to be, in this case, between 1 and 2, such that the derivative at c equals this f of b minus f of a over b minus a. Well, we already figured out that this is equal to negative 1 over c squared. Okay, and that comes from up here. All right, I've got negative 1 over x squared. I plug in x equals c, and I get this value. And I also have this comes up here. That was negative 1/2. So this is going to equal negative 1/2. Okay, maybe you don't like that in those different red and green colors there. So I don't know why. I just picked red and nice colors. So in essence, what I've got here, if I write this in black, I've got negative 1 over c squared equals negative 1 over 2. So now if I simplify this, I can cross, or some of you can just see that since the numerators are the same, I can set the denominators equal to each other. Either way, you'll end up with c squared equaling 2. And then if I take the square root of both sides, I get c equals plus or minus the square root of 2. Now I'm inside the interval. Remember that c inside the interval from 1 to 2. So c has to be between 1 and 2. So this tells me that c is going to be the square root of 2, which is approximately like 1.4, which is definitely between 1 and 2. Okay, c is not going to equal 1/2 negative square root of 2, because that's not between 1 and 2. So my answer is this. Let me just write it like that and erase this part right here. Oops. Okay, there's my answer. C equals the square root of 2 on this problem. Now, what are some applications of the mean value theorem? Well, there's a cool application in CGI, computer graphic imagery here. So what that? Well, let me show you some examples here. Let me get this to. All right. So here you should see an image of a figure. And in computer graphic imagery, in CGI, what we want to do is we want to take the figure on the left and we want to make it into an image that can be created by a computer. And what you do then is you go to the far right and you put on this triangulation of it. So you put on a grid on this character where you have these vertices and these line segments connecting. And to move the character, then you can use parts of math called linear algebra and matrix theory. And you can put each of the intersection points of the triangulation of that character. Each of those represents a value in a matrix. And if you multiply that, take those values and you multiply them by a matrix, you can move the character. Well, sometimes a character will have so many triangulation points on it that the calculations become really, really hard. And so what they did then in CGI is they thought it might be useful to try to reduce the number of triangular points. And one way you can do that, that's come up, I'll show you here in this representation, is that they would put like a mesh or a cage around the animated. So if they want to animate a horse here, they'll put this box or cage around it, and then they can put fewer number of points on the cage, so it would require fewer number of calculations to move it. You have a fewer number of intersection points on the cage than you would on the original character. But when you do this, just because you put the cage around the character, it doesn't mean that the character is going to move inside the box. When you move the box, there's no reason why that the character has to move it's and stay inside the box. In order to do that, you have to do some math. You have to add on some math, and that math is applying this idea of mean value coordinates. So you're using the mean value theorem here, or the idea of the mean value theorem, to put it so that when you move the cage or the box that is around the character, that the character will move inside the box in the same way at the same time that you move the box. So as you move the box, the character inside will move. And the reason for that is you've applied this mean value coordinates idea to the character inside the box, and then it moves automatically. I think this is really a cool idea that you can use this mean value theorem in this application on computer graphics to move characters in a more efficient way, because you have this box that requires fewer vertices and fewer points than does the number of boxes or number of vertices that you have on the character. And it's all possible in this case because of the mean value coordinates. All right, we just saw an example of how the mean value theorem can be used in an application of CGI to help move animated characters. Let's now look at another example in a mathematical setting. So here's a second example in mathematics. And the example here will be to show that the equation x to the fifth plus 10x plus 3 equaling 0 has exactly one real solution. Okay. Now, when we say real solution, that means there's going to be one value for x that we can put in there. Sometimes this is also talked about as having a root or a 0. So these are terms that be put in for solution here. So sometimes you'll see a homework problem or a test problem will say, show that this has exactly one real root or one real 0, or it could even have just has one real solution. So what do we do here? We have two parts here. Part 1 is to show there is at least one solution. And then part 2, show there cannot be two solutions. Now, if I've got at least one solution, but I can't have two solutions, that means that there is exactly one. So there's exactly one solution here. Some of you may say, well, what about if I have three solutions? If you have three solutions, then that means you're going to have two solutions also. And so you can't have three solutions if you can't have two solutions. All right, so to do this, let's look at these two parts. So part 1, again, we want to show that there's at least one solution. We're going to use the intermediate value theorem. So we had talked about this. The intermediate value theorem says that if I have a situation where I have a function that's continuous and continuous at endpoints, so we say x at a here equals a, x equals b, and this is y equals f of x. So we have f is continuous on a to b, and we use a special case of this one here, and that special case. And if f of a is less than 0 and of b is greater than 0, or vice versa. So you could have f of a greater than 0 or f of b, and then f of b less than 0. Then what do we get? The conclusion in the intermediate value theorem is that there is some c, where c is between a and b, such that f of c equals 0. Okay, this is a variation of the intermediate value theorem, but this is the most common one we've used. And you can see that in this case, my value here is going to be, there's going to be my c value there. So if my function is continuous, and for one value of it, it's below the x-axis, and one value is above the x-axis, then there has to be some place where it crosses the x-axis. That will show that there's at least one solution. If it crosses the x-axis, that's a solution to this. So what I need to do here is first define my function. So let's say define a continuous function. So I'm going to call f to be my x to the fifth plus 10x plus 3. And where does that come from? That comes from up here, that left-hand side of the equation. Okay, so there's my function. And then we know f is continuous. A whole set of whole real numbers from infinity to infinity, because it's a polynomial. And now I have to choose some A and some B where f of A is going to be less than 0 or greater than 0, and f of B is going to be the opposite one. So one of them is going to be greater than 0 and one's going to be less than 0. Well, when I do this, choosing 0 is always a good one to do. So if I choose 0, then I'm going to get 0 to the 5th plus 10 times 0 plus 3, which equals 3. So that's greater than 0. So now I need to find a number that I plug in here so that it will be negative. I'm going to choose -1. If I do that, I get -1 to the 5th plus 10 times -1 plus 3. That's going to be -1 minus 10 plus 3. That's going to be -8, and that's less than 0. So intermediate value theorem, IVT, is at least one solution, which we'll call x equals c, where c is between 1 and 0. And so we've got at least one solution. So that's fun. And again, we've talked about those types of problems earlier in the course. Now, here's the new part. Part 2, show there cannot be two solutions. All right, and we're going to use the mean value theorem, of course, because that's what section we're in. We're going to use the mean value theorem and a proof by contradiction. So we're going to use the mean value theorem and proof by contradiction. So what's a proof by contradiction mean? Well, that means that you assume what you're trying to prove is not true, and then you show that this leads to a contradiction. So proof by contradiction is you assume what you're trying to prove is false, and then you follow the logical steps, and then you show that this leads to something that can't be true. And so then your original assumption must be false, and that proves what you're trying to do. All right. Here's an example. Let me just give you a little here of this idea. Suppose person A is a suspect in a crime. Then a detective finds a photo of the suspect taken a video camera at a store that's 50 miles away and is at the same time of the crime. Well, can that suspect have done the deed? Could that suspect really be the criminal? No, because that suspect can't be in two places at once. Can't be at where the crime happened and be 50 miles away in the store where he was photographed. So there's a contradiction. You assume that he's the suspect, but then you find some evidence that shows that he can't be the suspect because he was shown to be somewhere else at the same time, and that the distance was too far apart for him to be at both places at the same time. All right, that's an idea of a proof by contradiction. Okay, so I guess I don't need to write that there. So what are we going to do in this case? So what we're going to do is we want to show that there is exactly one zero. We want to show is exactly one solution, or zero, or root. And we're going to do proof by contradiction. So we're going to, that this isn't true, that there isn't exactly one solution. Well, we already know that there's already at least one solution. And if there isn't exactly one, that means there has to be at least two. So we're going to assume that there is not exactly one solution. And again, like in part 1, we already showed that there's at least one. This means by part 1, there has to be at least two solutions. Okay, so we're gonna let's call the two solutions. One of them call A. One is x equals A, and the other one is x equals B. Okay, so if it's a solution, what does that mean? That f of A equals 0, and since B is a solution, f of B is 0. All right, so we're assuming that there is not exactly one solution. All right, we're going to do a proof by contradiction. So we're going to assume we're going to assume the opposite of what we're trying to prove. We're trying to prove that there's exactly one solution. So we're going to do a proof by contradiction and assume there's not exactly one solution. And since part 1, we proved that there is already at least one solution, that means then if there's not exactly one, there has to be at least two. And we're going to call these two solutions. One of them is going to be x equals A, and one's going to be x equals B. And if it's a solution, that means when I plug in x equals A to the function, I should get 0. And likewise, if B is a solution, that means f of B is 0. Okay. Now, since f is a polynomial, continuous on the interval from A to B, and it's differentiable. on the open interval from A to B. Why do we need to do that? Because those are the hypothesis by the mean value theorem. In order to use the mean value theorem, then we have to do that. We have to show that those are true. So now we can say by the mean value theorem, there is a value x equals c, where c is between a and b, such that we get the conclusion of the mean value theorem, the derivative at c equals f of b minus f of a over b minus a. All right, there's the conclusion of the mean value theorem. But what is f of b? Well, f of b is 0. So we know that. And f of a is 0. So we plug those back in here and we get 0 minus 0 over b minus a, or we get 0. So there has this value c, when I take the derivative and I evaluated c, then the value of it has to be 0. So f prime of c equals 0. Well, just like we've done with the other previous mean value theorems, let's compute for c, the derivative of f. Okay, what's the derivative of f? Well, okay, again, let me do that. It would help to write this down. So remember, is f of x is, in this case, was x to the fifth plus 10x plus 3. So now we're going to compute the derivative. So the derivative is going to be 5x to the fourth plus 10. All right, so now there's got to be a number, a real number that I can put in there for c, c equals x, so that that 5x to the fourth plus 10 evaluated at c is going to equal 0. Okay, so what number for x equals c gives 5x plus x to the fourth plus 10 equals 0? Well, there is no number that does that, right? Because look what we have here. X to the fourth, that's the smallest that can be is 0. That can never be a negative number. But we also have this plus 10. So we've got a number that can never be negative. It's either going to be 0 or larger, and I'm adding 10 to it, and I say it has to equal 0. Well, that's not possible. I can't have this, okay? This is not possible. You can't put in any number here for x so that you get 5x to the fourth plus 10 is going to equal 0, all right? Maybe another way to see that is, you don't have to do this, but another way you could see that, if I brought the 10 to the other side, I would get this. If I divide by 5, that would give me x to the fourth is equal to -2. What number can I put in that if I put it to the fourth power, I get -2? You can't. There is no number that does that. This is not possible. Okay, not possible. So what went wrong here? Well, it's like the example I told you about the suspect, and he was a suspect to a crime, and later they found a photo of him at a different site 50 miles away that happened at the same time. So he couldn't be a suspect. So what does that mean? That means that he can't be a suspect. So the original assumption that he was a suspect was not true. That same thing applies here. So that means the original assumption is false. And what was the original assumption? That is, the original assumption was that we had 2 roots, so or 2 solutions. We cannot have 2 solutions. All right. So there's our proof. We showed in part 1 that there has to be at least 1 solution. And in part 2, we showed that you can't have 2 solutions. Therefore, there must be exactly 1 solution. Exactly 1 solution. So here's an application of the mean value theorem. All right. Hope that helps you. Have a great day.